Hello and welcome back everybody, and we're back with the multiphase heat exchanger problem. Earlier we were done with finding the area of the subcooled section of our heat exchanger, and well, we're still a long way from being done. We still have to find the area of the saturated section and the superheated section. So we're only 2/3 done. So hopefully in this video we'll be able to get those two sections knocked out. Alright, so let's see what we know about our saturated section. Using the energy balance on the subcooled section, as we did in the previous video, we were able to find the temperature that was coming in to the saturated section for our process stream. And right now we don't know at what temperature this process stream is going to exit the saturated section. So just a small recap of what our heat exchanger configuration was looking like, the information that we were starting off with. So we have a number one, section 1 was our subcooled section, section 2 is our saturated section, section 3 is our superheated section. We know that our process stream must enter at 150 degrees Celsius, and the heating requirement, it must exit at a temperature of 180 degrees Celsius. We don't know these intermediate temperatures. Oops. But we do know that steam enters at 234 degrees Celsius. We know the intermediate temperature at which it becomes saturated and condenses, and we decided that we're gonna use 174 degrees Celsius as the final outlet temperature. Okay, from our calculations on the subcooled section, we were able to find this temperature. Now, in order to find the area of the heat exchanger, you need the temperatures at both the cold side and the hot side. So we're still missing this temperature. So what are we going to do to find that missing temperature? Well, once again, our two most trusted equations, the energy balance, we're going to knock that out first. So the energy gained by the process stream, which should be represented by this expression, 150.6, must equal the and this is a in this section there is no temperature change for steam. Steam is actually condensing. It enters at 184 degrees Celsius as saturated steam and exits as saturated liquid. So we're going to use the latent heat of vaporization instead of the heat capacity and delta T. Okay, so yeah, energy lost by the steam is going to be equal to the energy gained by our process stream. So if I just play around with this equation, I'm going to get 150.6 plus the mass flow rate of steam, which was found to be 1397.3 as we did earlier, times the heat of vaporization, which for our case is 2000. And again, this is the information provided in the problem statement. The molar flow rate and the heat capacity of our process stream were also given. So our temperature comes out to be, I'm doing these calculations real time for you guys, just like helps with the spirit of problem solving, keeps me on my toes. So 1000 times 100, I'm getting better at these, so you guys will have a much easier time as these videos progress. Okay, 178.5 degrees Celsius, that's our outlet temperature, the outlet temperature for our process stream in this particular section, 178.55. Okay, so we have all the temperatures both on our hot side and our cold side, so we can plug in the design equation to find the area of the heat exchanger. Our good old design equation, Q equals UA times delta T log mean. Q once again is going to be equal to either the you can use the flow rate times heat capacity of the process stream, or you can just use the mass flow rate of steam times the heat of vaporization. I'm just gonna use the steam. It's more convenient, like it's just fewer terms that I have to punch in to the calculator. And the heat transfer area is given in the problem statement. Notice that, like, you'll notice that the heat transfer coefficient is the highest. The heat transfer coefficients are much larger for saturated sections of a heat exchanger. Okay, so if I do this calculation real quick, we'll be able to get things rolling. Okay, so on one side, let's see, our delta T on this side is gonna be 184 minus 178.55. So the delta T on the hot side is 5.45 degrees Celsius roughly, and the delta T on the cold side is 184 minus 150.6, 33.4 degrees Celsius. Delta, I'm gonna call this delta T1, delta T2, and now we're just gonna take the log mean of those two. 33.4 minus 5.45 divided by natural log 33.4, or 5.45. Okay, so everything looking good so far. Just want to make sure I haven't made any stupid mistake. Alright, looks good. So let's just punch that into our calculator and find the area for our saturated section. And now is the moment where you guys hear the clacking of my calculator, whereas while I patiently work these problems out. Okay, so this area comes out to be 22.66 meters squared for the saturated section. Okay, so we're making some progress. We have the subcooled section, we have the saturated section. Now our final the final section, the superheated section. Okay, the temperature at which the process stream is entering the superheated section is going to be the same as the temperature at which our process stream is leaving the saturated section, this stream right here. And we just found, earlier we were able to calculate that, so which turned out to be 178.55 degrees Celsius. And notice that, like, we know the delta T on the hot side, and we know all the temperatures of the four streams, so we don't need to use the energy balance. We can jump right into the design equation and find the area. So hey, so delta T1 comes out to be 5.45 degrees Celsius, and delta T2 comes out to be 234 minus 180, 54 degrees Celsius. Okay, now the heat transfer coefficient was given in the problem statement. Q equals UA delta T log mean. I'm going to use the flow rate of steam times the heat capacity of steam, the temperature it takes to go from superheated to saturated, equals UA delta T log mean. And this expression comes out to be 1397.3 times the heat capacity of steam, not water, steam. And we're interested in the area, so our heat transfer coefficient is 2000, and our log mean temperature difference comes out to be, I'm gonna be higher minus lower, so I'm gonna use 54 minus 5.45 divided by the logarithm of 54 divided by 5.45. Okay, once again, the hardest part, punching in the numbers into the calculator. Ooh, all right, finally. Our answer comes out to be 3.47 meters square. So the total area of our heat exchanger is going to be the area of the subcooled section plus the area of the saturated section plus the area of the superheated section. We just found the superheated section to be 3.47 meters squared, and earlier we just found the saturated section to be 22.66, and earlier in the previous video we found the area of the subcooled section, 2.06. All right, and if you add all of that up, it turns out to be a total heat exchanger area of 28.2 meters squared, correct to 1 decimal place. So a couple of closing remarks. In this problem, we selected the so the variable that we picked was the outlet temperature of our hot utility. We picked the outlet temperature to be 174 degrees Celsius. That was the number that we based all of these calculations on. So let's say if you were to like vary this between 174 to 184, or actually let me say you were to like do a parameter sweep of like the hot outlet temperature from, let's say, 151 to, let's say, 184 degrees Celsius. This becomes an optimization problem. As the so for the as the hot outlet temperature decreases, the area of the heat exchanger is gonna increase because the driving force, the delta T on the cold side, is gonna go down, and your steam flow rate is gonna go down. Your heat exchanger area is gonna go down. HX area goes up, sorry, but your steam flow rate is gonna be lower. Whereas on the other side of the spectrum, your heat exchanger area will be smaller, but your steam flow rate will be higher. So it's a trade-off. And once we have the tools for process economics, we're able to quantify the capital investments of purchasing a heat exchanger, and we know the operating costs associated with generating using hot utilities such as steam. We can define a cost function, and we can minimize that by varying this outlet temperature. So yeah, that pretty much sums up this video, and I'll see you guys next time.